Welcome, everyone, and thank you for joining us today. My name is Paul Donahue, and I will be your host. We ask that you please keep your device muted during the session, and if you have questions, please direct them to me via the chat function. We'll do our best to answer questions at the end and to follow up with any unanswered questions via email. As I think you know, these tech talks have been designed to provide straightforward insights into radio frequency components, the related technology, and the extra design and engineering value that is added by a custom manufacturer such as Quantic TRM. To begin today's session, I'm once again pleased to introduce Quantic TRM's Chief Technology Officer, Shaun Moore. The author of 2 U.S. patents and a number of white papers and technical articles on passive microwave technologies, Shaun has been with Quantic TRM since the late 90s, and his passion for the job and for solving problems has only increased over the years, especially when it comes to resolving our customers' design and engineering challenges. So welcome, Shaun. Can you share an overview of today's topic and your objectives for the session?
Yes, thank you, Paul. So today, I'd like to talk about high power products and really what differentiates them, and what design changes do we need to make sure that they survive their environments. So we're going to open up today by defining really what constitutes high power. What does high mean? What does low mean? There's kind of a vague word there, but we'll define what that means for passive microwave components. We'll then go ahead and we'll say, well, once we achieve those requirements for a high power device, what sort of design changes do we need to start making to accommodate those higher power? And then once you start making changes, there has to be some other negative that happens. And basically, we'll start talking about what are the parameters that are affected by the changes that we start to make. We'll then go through some Quantic TRM differentiators, and then we'll sum it up.
Well, that sounds good. And maybe to get started, what exactly is the high power threshold?
Sure. So the high power threshold really comes down to if you have a standard sort of construction technique, there's a certain amount of power that they can naturally handle without really doing anything special. And that's kind of the threshold, is not doing anything special. So for distributed technology, which is things that are in either strip line or microstrip, for example, a Wilkinson power divider, or for a 90-degree hybrid or a 180 hybrid or something like along those lines, the threshold for power dividers usually hangs right around 30 watts, which is actually still a fair amount of power. But anything below that, the construction really doesn't change at all if you go to build that. For hybrids and directional couplers, the power jumps up to about 50 watts, and that's primarily because a 90-degree hybrid or directional coupler does not have an internal resistor, either as part of a balancing network or a termination into it. So it's that resistive element that is the limiting factor for a Wilkinson style power divider. It's not the microstrip construction. So those are kind of the general thresholds that you have for that sort of distributed kind of technology. Now, for lumped element technology, which is where we use wire wound ferrites and capacitors to create the circuit elements, and this is used primarily for much lower frequency components. These components are typically run between kilohertz frequencies up to about 2 megahertz. It's a great construction technique because they are fairly compact. However, the power limiting on those devices for the sort of standard components is much lower. That's right around 2 watts for power dividers, maybe 5 watts for a directional coupler. The heat limiting factor here has to do with the ferrite beads that are in there. Most beads that are used in very kind of conventional broadband sort of lumped element construction techniques use a very small ferrite bead, and the flux density in that bead just needs to be managed. Once you exceed a certain amount of energy in the bead just overheats. And for a small bead, it doesn't take really a whole lot of energy to do that. So and basically, the bottom line is if you're talking about devices along these lines that have a higher power requirement, then you have to start thinking about them a little bit differently, and therefore they fall into the high power category.
So then when products exceed the threshold, what does that mean from a design or a construction perspective?
Sure. So for distributed constructions, and this is for microstrip and strip line, things that we need to start thinking about. And on this slide is sort of set up here for things on the left-hand side are really sort of what happens, what you need to be aware of, and things on the right-hand side of this slide talk about what changes need to be made. So if you think about the first couple of bullets there, we're talking about heat buildup substrate. Once we exceed 50 watts, we have to be very careful about thermal dissipations because we start building up heat due to copper losses or loss tangents in the dielectric. Also, most PCBs that are used for microwave construction really don't have very good thermal conductivity, and therefore any heat that builds up on the copper trace kind of stays there. It doesn't dissipate really all that well. So what does that mean? And so for a PCB, well, one of the first things that we need to start thinking about is, do we need to go to a thicker PCB? If we go to a thicker PCB, that allows the circuit traces to increase in width. Also, sometimes going with heavier copper will also increase the cross-sectional area of the copper trace, which will reduce the copper losses. A secondary benefit of going to a wider trace is now we are now increasing the surface area that heat can dissipate through the dielectric, and therefore making the heat get away from the copper a little more effectively. Also, we can also go in there now and start picking materials that have a little bit better thermal conductivity. So these are the sorts of trade-offs that we can do. I mentioned earlier, speaking about thermal buildup in resistors and Wilkinson power dividers. Well, what happens there now is we need to go to larger resistors. Larger resistors do have higher parasitic elements to them, which are undesirable, especially in a Wilkinson style power divider, for example. Theoretically, a Wilkinson power divider needs zero length between its nodes, as well as you do not want any reactance to ground from the resistive film. As soon as you start going to a larger resistor or one that has a good heat path to ground, you now have a straight capacitance to ground, which is something that really degrades the performance of the overall Wilkinson power divider. And as a result, really, that makes a high power resistor in a Wilkinson a very undesirable construction technique. Something else to start thinking about is corona breakdown. Once you start exceeding higher voltages, you have to worry about just arcing inside of the part. And in order to help mitigate that, we just start going with a little bit larger sizes, larger gaps. And of course, when you start going to larger gap sizes, that really limits your high-end frequency, because then you start getting resonant modes, which certainly are a very negative thing. And as I sort of alluded to a few minutes ago, we get into restricted topologies. Some topologies, like I mentioned with the Wilkinson power divider, just don't do well once you start adding those parasitic effects of the resistor. The bandwidth of what ordinarily would be a very broadband, sort of good performing Wilkinson power divider, all of a sudden we start adding those parasitics to it. Becomes quite unwieldy and very unpredictable as far as to how it's actually going to perform. So it's usually not a good idea to stay with that sort of technology.
Okay. Now, I've heard you speak of lumped element construction. Is that applicable here in some way?
It is too, Paul. It's very similar as far as to how the effects are. Again, we have to worry about heat buildup. The first item listed here is ferrite cores. Larger cores, when you're dealing, for example, with ferrite cores, you have to look at what the total magnetic cross-sectional area is and how much flux density that core can hold before you saturate it with energy. So therefore, when you go to higher power levels and more energy is being coupled into the core, It's not so much a heat problem as it is a flux problem. You just need to get a bigger core so they can handle more flux. What happens when you overload a core or put too much energy into it that the core can actually absorb, it just gets hotter than a pistol in a heartbeat. So that becomes a serious problem. Problem with going with larger cores is that especially the stray wire capacitance really starts to become significant. Magnetic and inductors really don't want to have any capacitance in them at all. And the longer the wire run is, the more interwire capacitance that you get, and the more capacitance that you get between the wire and the core, all of which create a tank circuit, which just narrow bands the device. So that is that's a definite thing that needs to be considered when you go to higher powered devices that have that. Heat buildup and resistive elements. Again, this is a similar discussion as to what we had for the distributed elements. Again, once you start going to larger physical resistors, you have to start looking about parasitics. Same problem with corona breakdown and the restricted topologies. Like I said, with lumped elements as well, there are certain topologies that as soon as you get larger and larger with higher power, you certainly have to go in there and start really limiting your choices for what will function. Here specifically, I think, in addition to the distributed element discussion, the topology limitations are actually a little more severe than what we have for the distributed elements. Here, when you get into either wire wound inductors or using coaxial structures to help build these transformers, the stray reactance off of the larger wires and cables really becomes very significant and something that definitely needs to be accounted for when going into the design.
So could you speak maybe a little bit more specifically on how these construction variations impact performance?
Sure. So really, one of the first things that you need to do when you go into a higher power design is the parts need to get larger. Heat will build up and it has to go somewhere. So therefore, we have to go into larger components, which again add to parasitics, which really help limit sort of bandwidths that you can cover with this. Other problems that come up with higher powers, you have to worry about corona breakdown, or flashing over. You have to worry about heat, because now we're putting more energy into the system. Any losses in the system will all be converted to heat. We have to get the heat out of the system. We do lose bandwidth. Like I said, as soon as we go to a higher power sort of design, inherently due to the increased parasitics that are there, bandwidth is going to be reduced. An example of that is for a low power ferrite based power divider, for example. We routinely build those power dividers with 100-to-1 bandwidth. It's kind of just that's how much bandwidth you get out of them without really struggling very hard. We routinely get 100-to-1 bandwidth out of our small low power devices. I'll say that once you go up to say 100 watts or so, if you get a 10-to-1 bandwidth out of it, you're doing good. And when you go even higher in frequency, the bandwidth continues to drop. So it's a real struggle, and it's a real problem that we have as devices want more and more bandwidth at higher and higher powers. We very often you find yourself at odds being able to build a part that will survive the power and also accomplish the bandwidth. We need to make sure that we can get the heat out of it. Therefore, on certain designs, we have to no longer rely on just passive sort of heat mitigation. Very often we have to either have liquid cooling or fans or other sorts of heat sinks in there to get the heat out of it. One thing also that I think is really important is that if we're especially building high power combining circuits, very often people don't really consider the exact nature of the signals being combined. And that makes a huge difference as to the amount of energy that's going to be dissipated inside the device. So I think it is critical to fully understand the nature of the signals being combined. Are they phase coherent? What sort of variation do we expect to see? How much of an amplitude variation do we expect to see? These are all things that really make a huge difference in how much margin that we have to design into the power combiner so that it can safely survive and perform over its mission life.
Well, great information as usual, Shaun. So finally, what are some of the unique aspects or differentiators that Quantic TRM brings to the table with respect to high power products?
Sure, Paul. So one of the biggest things that I think I want to bring up here is we want to work with the customers. We want to be a solution provider for you. And I think that comes down, I think that really is one of our big differentiators. We want to work with you. We want to discuss, what issue that you're having and how can we best modify our part so you end up with the best product for you. And it could be anything from a very custom design, different mounting, different qualification testing, for validation, or sometimes it's just data that you need to do, and therefore bring the over higher value for the whole program over to what your needs are. TRM really does a good job of being very careful about selecting materials to make sure that the materials that we use to design the product will meet the power and will meet the environments that the design needs to be in. We have robust mechanical packaging. We like to test and provide the objective evidence that the part does meet your requirements. And really, the bottom line here is we want to be your solution provider. So think of us as a free consulting service for passive microwave components. And we'd like to work with you to make sure that the part that we deliver is the part that you need.
Okay, terrific. So we do have a question, and it's, what do you suggest or recommend for program engineers to do during the early stages to make a determination about the use of high power products or components?
Yeah, it's a good question, Paul. So I think the one thing I think that put it in a nutshell is to make sure that we understand the nature of the signals that are coming in and understand not only the nature but exactly the phase relationship between the signals, the bandwidth, the duty cycle, all those parameters that are really going to drive how much heat and what sort of a breakdown issue that may be having. And if we're talking about power combining, to go in there and make sure we understand the phase relationship between all the signals. One thing that I have seen over and over again is that system engineers ask for a bulletproof design. And very often that can be done, but at a cost. And once they actually go in there and they take a look at what both the size of the part and what the cost of the part is, once they pick the jaw up off the floor, we then start having a serious conversation as far as to what they really need. And very often what they need is not a bulletproof design. What they need is a part that's going to function in the system, and making sure that they understand what all those inputs are, and that then this way we can then have a good, honest conversation as to what the ramifications of all those are, so we can actually go in there and buy and build the most effective design. And the most effective design very often it is one that fits in the system and can service and do its job over its life. Specing something that is bulletproof very often results in a part that's too large to fit into the system, and that doesn't do anybody any good. So we have to make sure, though, especially for these high power products, that we understand the nature of the signals that are being fed into it, so we can do a proper design of the component to make sure that we can fit it, that the part can fit into where it needs to be, and still be reliable and function.
Okay. Well, thanks again, Shaun, and thanks again to all of you for joining us. I think in summary here, the bullets on the screen here echo Shaun's comments about Quantic TRM differentiators. And going forward, if you are a customer and you have more questions, or if you'd like to discuss details with one of our engineers, we'd love to hear from you. Please feel free to call out the engineering hotline. The number is on your screen, 888-677-6877. There are no costs associated with these calls. And if you're one of our field sales representatives, then you know that your calls are always welcome. And you can also submit questions directly through the sales rep portal on our website. In case it's helpful, the next Tech Talk will be on Tuesday, February 21st at 1 p.m. Eastern, and the subject will be multi-octave beamformer networks. Thank you all, and thanks again, Shaun.
Thank you, Paul.